In most high school chemistry courses, there are 3 periodic trends that everyone tries to include in their curriculum: atomic radius, ionization energy, and electronegativity. Now, I'd say it's also very common for teachers to approach this as a fact-based lesson. This is the trend, and now practice it. And also to group them together as a lesson on periodic trends. And then do all of this skill and drill style practice, many questions, this or that, which one's bigger? This or that, which one ionizes more easily or takes more energy? This or that, which one's more electronegative? And in a teaching style that is very teacher-centered, I guess that would be okay, because what we're wanting to do is transfer knowledge to a student into their brain and then have them use it. Unfortunately, that's not how learning works. We work on a progression where we learn, we recall, we use, we create new knowledge eventually. And so if you are of the mindset where you would like to go in a more inquiry-based direction with your teaching, with your students' understanding, if you are required to use 3-dimensional standards, the NGSS, or some state adaptation thereof, or if you've just seen CER out there, claim evidence reasoning, and you feel like it can do more for your students than just be used as part of a lab activity, this video is for you. In this video, I'm going to show you actually the very lesson I used to address atomic radius through exploration, and as a launch pad from the Bohr model into more sophisticated models like Schrodinger's model. If we haven't met before, my name's Lisa, and I have taught chemistry online for nearly 15 years. It has been a struggle, but the way I was able to be happy, frankly, in my job as a science teacher who actually loves to teach science was to step away from the status quo, not rely on this lecture lab mentality, because frankly, I couldn't do wet lab. And when I opened up my mind to the fact that science is so much more than that, I created a curriculum where every single lesson students are observing, they're using their observations as evidence, they're able to cite that evidence through their analysis, come up with unique inferences, and almost every class period create new knowledge. So if that sounds like something you're cool with, let's get started. Before I begin, hop right into my lesson, I do want to tell you a little about how it's aligned. When I approached my curriculum preparation, I was thinking science as practice. I was thinking science is observing the world, asking questions about it, doing little tests, learning things in this constant iteration. And then down the line, I learned that NGSS is a thing, the Next Generation Science Standards. And they have it all laid out with this idea of science and engineering practices, actual fundamental science practices that we want to impart to our students, and cross-cutting concepts, really ideas that underline all of science. And it's in these 2 features of a lesson that I think we are creating scientists rather than scholars. So I want to tell you about the science and engineering practices and cross-cutting concepts that come alive in this particular lesson. If you use NGSS, if you are using some version of that, I am in Pennsylvania and soon required to use the Steele's iteration of NGSS. The standard we're working with here is the one that pertains to structure and properties of matter. It reads, using the periodic table as a model to predict the relative properties of elements based on the patterns of electrons in the outermost energy level of atoms. Now, as a chemistry teacher, you know that there's a whole lot in there. And so we're just hyper-focused today on atomic radius and the periodic trend, because that standard is all about patterns of electrons and using the periodic table, relative properties of elements. So in this lesson on atomic radius, and more specifically, The atomic radius exploration I've planned out and the whole lesson I've designed around it is not just a lesson where students focus on one science and engineering practice. Typically in your three-dimensional standards, they are calling out just one practice to focus on. And certainly you can focus there. But what I want you to look through for as we go through this lesson is the use of models, developing and using models. Now, you can't really teach chemistry without models. So that almost goes without saying. It should be there at the forefront, and it is. But also, because every lesson is as observation focused as possible, we're always collecting data, whether it's qualitative data or quantitative data. In this lesson, you will see quantitative data, and you will also see students interpreting that data to actually annotate the periodic table with the trend we want them to see. So we are not telling them the trend. In fact, they are discovering it for themselves through this process of observing and learning. In so doing, they're obtaining, evaluating, communicating information, and engaging in argument from evidence. Though the way I teach the lesson, we do that as a group because I do not teach an honors level of student and I don't teach an advanced placement level of student. If I did, I'd probably charge them with really coming up with those evidence-based arguments. This is something for me I have to do as scaffolded questioning after our atomic radius exploration. Okay, and as per cross-cutting concepts, now science and engineering practices, these are the things the students are doing in this lesson. In the cross-cutting concepts, what are the underlying ideas and philosophies, basically? There's a lot of relationships here in the cross-cutting concepts. In atomic radius, we are, of course, having to address patterns because that's central to the standards. It's the pattern of the periodic table, and it is periodic trends. That's what we're going after. It's one of the big three. So, but we are also looking at scale, proportion, and quantity as obvious. We're looking at a size component of atoms, the radius, and we're going to be comparing one bigger to another, bigger than another, or ranking in order of size even then. So this is at the forefront also, and system models. The basis for atomic radius is going to be, when we get to that E and R of a CER response, the evidence and the reasoning, it's all going to be about how many orbitals there are. It's all going to be about that effective nuclear charge, something I like to call proton power, and the strength of that nucleus to pull in electrons and have that electrostatic attraction. Now, without giving a nod and making that front and center, the component parts of the system, we can't get to the why. So those are things you're going to see that are deeply built into this lesson. The other thing I'd like to point out also with this is that I teach this lesson directly after I teach the Bohr model of the atom and the concept that electrons live in orbitals, but they don't circle around the nucleus like the planets around the sun, and rather they are bouncing around, and there's direct phenomena that come from that. But in the bouncing around, there is already a focus on the orbitals. And so I would recommend, if you're going to use this lesson or create one like this, that you do make Bohr's model of the atom a showstopper before you come here. It's kind of required prior knowledge, I think. And as per required prior knowledge, I set out all my lessons with what I like to call a review and preview. It is my warm-up tool for the lesson. And in fact, we have 5 parts to pretty much every one of my inquiry-based science lessons. They start with a review and preview. And I call it that because students will pull their information that they've already know that required prior knowledge, and connect it to almost be able to see or predict what's going to happen in this lesson. So there's that. And then we have some clear objectives that students can track for themselves. I use learning intention success criteria so students are able to monitor their own learning, see what they should be checking off the list and what they haven't, be able to gauge where they're at even on a progression of mastery versus, approaching mastery. Then we have clear task instructions so students can do the activity, which is typically technology based. Anytime we can get a student controlled simulation is super. Second to that would be a video where we can maybe pull parts from it and have students do something with that. And thirdly to that, I'm going after a text. But the notion there is students are always hands-on, virtual hands, not their real hands. We're not actually having to go to the dollar store and buy any kind of doodads to get this done. All digital. We go all digital. And then an artifact. And the heart of it really is in the artifact, as you'll see here, because if the artifact is created in a way that allows more easily the data to show the pattern, to show the connection between something like cause and effect, or how the parts of the model influence one another, then you're going to get there faster. You're going to get there easier with your students. And then finally, we want to do some data-dependent analysis, and that comes from the artifact. So the construction of the artifact lends itself to data-dependent analysis. And then finally, skill practice. So again, where this lesson stands out versus some others is that we are not getting to the practice. We're not asking the students to do the thing like fluently until we can understand, we can make a claim, cite evidence, and determine some reasoning. We go deep first so that everything at the surface then can be pretty straightforward, dare I say easy. And the thing about atomic radius also as a periodic trend, well, you know that if you understand that deep level, you can actually use atomic radius to explain as reasoning why an atom has a higher or lower ionization energy, why an atom has a higher or lower electronegativity. So specifically, the atomic radius and understanding that feeds into the rest of the very cumulative nature of a chemistry curriculum. Okay, without further ado, we're going to take a look at this lesson. Now we're starting, here's the review preview. We have 3 elements. Now these actual 3 atomic models, they do come from a practice I assigned at the end of the Bohr model exploration, the Bohr model activity, where there I just had them count the number of valence electrons, count the number of what I called core electrons, and identify the elements. Still cycling back on what they knew about atomic number and using the periodic table in that way. There is some of that here also, so I would say you probably don't need to have done that practice first. I'm asking students to pretty much move left to right here for every atom to name it, looking at that number in the number of protons in the nucleus, determine its identity, get familiar with its symbol also. And while they're looking at the periodic table, refresh that group and period concept and find this exact location. Now I am asking them to use A numbers, our main group elements, because as you know, these numbers are much more helpful than the teen numbers. And this is very, very important to the data analysis for the review and preview. Truly, folks, the review and preview is like its own activity here because it does reveal something quite big. I frankly should make it a separate lesson, but it's here for you, so enjoy it. It's one of those ways that I can bring you enormous value in the products that I create. Okay, so the name, the symbol, the group, the period number, then using evidence from the image to cite the number of orbitals and the number of valence electrons. Now, this is how that will work out. So what students should be able to see when I ask them, based on this data you've collected, what do you see in terms of the periodic table connection to the actual model? And what they should be able to notice is that the number of orbitals match the period number. The number of valence electrons match the group A number. And so we can draw Bohr model atoms using just the periodic table as a reference. And this is where we can summarize that for them. Definitely going on to say this doesn't apply to our transition metals or our special groups beneath the periodic table, but in general for our main group elements. And then I have always asked students to practice this, for everybody to choose an element, list the group and period number, and draw it out. I did used to have this sort of grouped with the rest of my activity, and I have since pulled it out as a standalone activity. I, in fact, would recommend this. This year I've used it as a bridge between my basic Bohr model lesson and my atomic radius exploration, because I think it just allows students that more time to process and practice. The other wonderful thing here is if you use a great technology tool, if you're using Google Classroom and you can have all of your students in one document, but each on a different slide, then they can all see what everybody else is creating. And you can view models of so many elements. You'll have really ambitious students who want to build like iodine, and then you'll have your skate by it students who want to build hydrogen. But the reality is, no matter who's building what element, as long as it's aligning with this principle of group number and period number telling us valence electrons and orbitals, then they're learning. And you'll know if they're copying from Google, because they'll fill in those core electrons, where here we specifically don't want that. Because I tell my students, who cares about core electrons? They don't do anything in chemistry. We care about those valence electrons. And that's what we're going to be citing as evidence and reasoning for all sorts of chemical reactivity and chemical change phenomena going forward. So throwing this out there for you, this is like super bonus. I have also included a potential extension activity here where thorough instructions for it, and you can edit these slides if you purchase this lesson. I'll give you instructions later to purchase this lesson, or you can check out the description below for links. You can grade it any way you want. This is what I have recently done. But what I have them doing is creating 4 models on their own using these guidelines for drawing. In a sort of gamified way. I purposefully want them to choose 2 metals and 2 non-metals. I don't want them to get like picking ones that probably are going to cause us a little bit of a headache. So I do give them choices. If you chose that, then draw this. But then some follow-up to that. I've asked them to compare 1 and 2, which is bigger, citing evidence and reasoning, and 3 and 4, and 1 and 3, or 2 and 4. So the idea here is they're going to compare 2 metal atom sizes to non-metal atom sizes, and a metal versus a non-metal, which you and I know our metal's always going to be bigger, and what those reasons are. So that's a super bonus, but you might want to give that extension after this lesson, after you deliver this lesson, because it is size-based and they do require evidence and reasoning. So it's an extension of the preview, and it's an extension of the radius-based focus for this lesson. Let's talk about the radius-based focus for this lesson. Today we are learning how to compare the size of various atoms. I like to stop students right there and say, notice that I didn't say we're learning about atomic radius. We're not learning about the periodic trend for atomic radius. We are learning how to compare atomic radius or size with distinct goals of being able to use the new language, the new terms that we're learning to communicate with each other, and also to use as evidence later on and reasoning how the size influences chemical properties and participation in reactions. Our learning intention is always a bigger idea, a bigger why, a bigger end goal over weeks, maybe months. Success criteria, however, being much more focused on the here and now, what we should be able to accomplish today, or maybe over a series of 2 days, maybe even 3 days. And oftentimes you'll see in success criteria a mix of activity-based success criteria, because I want students to acknowledge what they're going to do in this moment, what they should be able to accomplish, in this class, in this deeper thinking, inquiry-based science realm, and what they should be able to do come test time. Because the fact is, for most of us, if our students are taking science, chemistry in the high school, they are going to go on to some program in college. And if they should encounter this again, we want them to have some recollection of these skills. So in this lesson, you can expect it to help your students use the terms periodic trend and atomic radius correctly in context, to have a conversation with you, to read and write about them, to describe the location of elements on the table using group and period numbers. Check, we just did that in the review and preview. Draw Bohr models using the periodic table as a reference tool. Check, we just did that in the review and preview. So we've kind of, I don't want to say it's half the lesson done, but maybe a third of it. Maybe a third of it. And I see this as integral to SEIs because it's a problem-solving tool students will have actually on their assessments to be able to draw it out and get back, always get back to that orbital, number of orbital concept, if not the effective nuclear charge one. So more focused goals for atomic radius exploration would be comparing the size of atoms of different elements and using the periodic trend that they pull out to compare size of atoms in the future. And both of those, numbers 4 and 5, I would say are assessment-based skills, but is something we're going to offer at the end of the lesson as a sort of formative assessment for our performance also. We have a quick word wall here just to remind students the significance of that valence electron. That's really the piece that comes from the Bohr model activity that I've described, and how they get the highest energy. Why are they the highest energy? Outlining here and usually setting up for my students that this is the first of a few periodic trends we're going to learn, and just putting that focus on the periodic table as a super powerful tool for problem solving in chemistry. Also pointing out that the size of an atom is not measured by diameter, circumference, mass, or volume, but radius. Because if we want any of those other things, except for mass, we can use the radius to get all the other things. But also, this also focuses us on the number of orbitals and how influential orbitals are to atomic radius. And potentially all those other features too, ionization energy and electronegativity. All right, next up is our main activity. Now, this activity, I am directing students to an active link and a well-respected website. It's a trusted source. I wouldn't call it necessarily a simulation, as it is an interactive tool. It is an interactive periodic table where you can click 2 elements and see the Bohr models, but also record 2 values beneath those models. You can record the ionization energy, and this is the tool I use for my ionization energy lesson as well, but you can also record the atomic radius in picometers. So being able to do 2 things here, your students will get the qualitative observation of seeing big and little, big or smaller, and they will also be able to collect the quantitative data to use as evidence toward arguments later down the line for actual atomic size. And as I mentioned, oftentimes to get your students to that next level, to get them to using evidence to explain, engaging in that argument, and doing the analysis that sometimes feels so big and so difficult, it really lies in the construction of an artifact that is amazing. I'm a little partial here. I feel like the artifact is amazing. Giving them on this digital tool, whether you're working in a Google Slides or I love to use Seesaw. I will drop a link in the description below to my EdTech Essentials guide where I talk all about Seesaw, why I love it, and get you started on your first activity there. I give them this periodic table so that they can annotate it. And I'm giving them spots, specifically not spreadsheet table style, because spreadsheets feel so adult. They feel so sciencey and they feel so heavy, and we don't want that. We want to take it down a notch, lower the stakes for our students, increase their confidence, and we get a lot better cooperation that way. I've experienced. So what I want them to do here is use lithium as a cornerstone. We're going to compare everything to lithium. We're going to look at the elements below lithium, sodium, potassium, rubidium, and cesium, and collect their sizes. We're also going to collect the sizes of carbon, nitrogen, oxygen, and fluorine. Now, we're doing a good job of covering most of the metal elements beneath lithium. We're not doing all of period 2. And I think that's okay. Definitely something that will come out here in that way is the metal versus non-metal piece. And we want that. So reiterating for the students, giving them a nod here that we're in the same group in group 1, we're in the same period in period 2. Once they collect the numbers, the quantitative data, then I'm asking to actually make it usable. Give us a visual indication of what that means or how it goes and what it is. And make, if I can use a program where I can highlight, I prefer highlight. But I've had to use Google recently, Google Slides, and so that's hard to do in Google Slides. So I have them circle. Circle the elements that are larger than lithium with a different color than those that are smaller than lithium. And as this is an editable PowerPoint, if you don't love blue and green, you could change those colors if you purchased my lesson or if you're devising it for yourself. And this is what that data looks like. Naturally, you would expect we see sodium, potassium, rubidium, and cesium all larger than lithium, and the nonmetals all smaller than lithium. Now, when students are finished and you pull them back and you're monitoring their progress and they're working in either small groups, there's the flexibility here for them to work in either small groups or as an individual. We can talk now as a whole group, or you can prompt them to come up with a basic lesson learned in their small groups. What happens to atomic radius as we move down? It increases. What happens to atomic radius as we move across? It decreases. Now, be careful with the terms increase and decrease. We definitely want to use the term radii rather than radius, which is actually pictured here, because radii tells us about more than one atom, and we're comparing the size of more than one atom, and it is not one element that is inflating or deflating or changing its size. I have to be very overt about that potential misconception in the wording here. And so just a nod in case you might consider that also. What I tell students though is now this is the evidence. Okay? If we were looking at which is bigger, lithium or cesium, we're going to say cesium. And the evidence is it's lower on the periodic table than lithium. That's clearly what we've uncovered. But that's not why. The periodic table, if it was never organized, never existed, cesium would still be bigger than lithium. So the reason is deeper than that. And what I do is I take snapshots from that interactive periodic table, from that tool that I had students look at, and I put them all next to each other here so they've got both the qualitative and the quantitative side by side, all of them, which is not accessible in the simulation, and asking them what's the reason. And this is so big for students, which is why it's so great to just encourage them to go back to basics. What do you see? What's in the observations? And they will tell me there's more particles in cesium. Of course there are. But let's be more specific. There's more electrons in cesium. Yes. Where do electrons live? Orbitals. Aha. And we're measuring radius. So this distance is going to be so much larger for lots of orbitals than smaller orbitals. And then we can summarize that. Of course, I don't think it really goes that smoothly. You shouldn't expect it to go that smoothly. There's a lot of pulling that can happen there. But it's brainstorming nonetheless. And I think it's fantastic whenever you have, this is the potential for your aha moment right here. Reminding students that orbitals are mostly empty space and they don't even exist if the electrons aren't there. So if electron gets lost, the orbital disappears. May or may not be something you want to interject at this time. We also go into the why of the nonmetal shrinkage. We put all of these models here because, again, cross-cutting concept is really systems and system models in a big way. Developing and using models, science and engineering practice for this lesson. We can cite the evidence that is the periodic trend. Fluorine is to the right of lithium, therefore it is smaller. That's what we would do in a skill-style drill practice. But if we want them to understand deeply why, so that they can go on and use atomic radius as a reason for chemical reactivity in the future, we need to get to it. And this one is tough. Here we say, but wait a minute. And if you have really astute students, they're going to look at this and they're going to say, wait, what if they're in the same period and there's the same number of orbitals? And you can walk right into that and say, aha, I got you covered. This happens. Why? And when you ask them now, what do you see as the difference? Now we don't see orbitals as the difference. Usually my students are still pointing to the number of electrons being the biggest difference. But then it gives me an opportunity to reiterate electrically neutral and the significance of that proton number. Then I make the very shallow analogy to Spanx. And I like to call this proton power. I don't require my students to know effective nuclear charge. We have at this point studied the nucleus, however, and we've studied that strong nuclear force that is the repulsion and attraction. Because again, those really astute students are going to be like, how come these negatively charged electrons can be all in there with each other? Why is that favorable? Because again, we've done another lesson, I'll drop in the description, that is just all about electrostatic attraction, and that opposite charges attract and like charges repel. So I wave my hands here a little bit because we don't have to go into that depth, and I'm just not interested in it. I like to call it proton power because the stronger the mama nucleus is, the better she could keep her kids all in close, keep tabs on them. And Spanx works great too. You know, Spanx strength 9, you're looking pretty skinny. And without them, is not quite as pretty. All right, the last leg of our lesson here is all about skill practice. And so it is what you would expect and maybe what a more conventional lesson or worksheet style resource would provide you, which is bigger. 2 elements in the same group. Again, which is bigger? 2 elements in the same group. Then we shift to 2 elements in a period, making sure that we're applying these concepts all along. First, we're looking at the number of orbitals for which is bigger, and then we're looking for the proton power, which is bigger. And trust me, this takes time and repetition, but it's so worth going over that reasoning and over the reasoning and looking at the evidence. Everything in your brain wants to say 35 particles take up more space than 34, but it just doesn't work that way. I like to give them this snapshot at the end for those with photographic memories, and they can kind of see it in their mind's eye. It also reinforces that idea that our transition metals don't really apply to this quite so reliably. In these lessons, I'm always providing, if you purchase a lesson from me on my store on TPT, you're always getting a digital worksheet too, which matches the entirety of the PowerPoint lesson. So you can use it if your student is absent or you're going to be absent. Your students can totally do this in your absence. You might have to come back the next day and iron out some wrinkles though, for sure. You can purchase this lesson in my store on Teachers Pay Teachers, but it does also come as part of my micro to macro full year curriculum, where you can expect to see, I would say 97% of every lesson that's there has this inquiry-based exploration style, just like this atomic radii exploration that we did today. Thanks so much for your time, and tune in again, where next time we're going to talk about Schrodinger's atom, orbital diagrams, and electron configurations.